Now we're going to go over some general characteristics of polynomial functions. So here, just a reminder, this is the general form of a polynomial function. This is the highest power. This is our constant, and this right here is the leading coefficient. So graphs of polynomial functions. Playing with my pencils here. They're continuous, so a reminder again. They're smooth and they sometimes contain hills and valleys. A turning point occurs whenever the graph changes from increasing to decreasing or vice versa. The y value at the turning point is either a local max or a min. Okay, so types of polynomial functions. So we have a constant function, f of x is equal to a, and a cannot be equal to 0. The degree is 0. So here's the reason why the degree is 0. If I put here times x to the power of 0, that's where technically the 0 is coming from. This 0 right here is because x to the power of 0 is 1, and 1 times a gives you the a that we had originally. Okay. The graph is a horizontal line. It has no x-intercepts, no turning points. So another name for f of x is y. And let's just say, for example, that we have y is equal to some number, and we'll say that it's 3. And so if I say here y equal to 3, it's technically a horizontal line. And so a can be any number, not just 3. And it doesn't have to be positive, it can be negative as well. So I put it here. It could be whatever value here, positive or negative. Okay, so let's look at these graphs. So the end behavior, I put here that it's a. Why is it that it's a? So we're going to start writing here. The left of the graph. So the left of the graph is technically as x goes to infinity. As x goes to negative infinity, excuse me. The left of the graph is the same thing as x goes to negative infinity, then f of x is technically headed towards a. And so here I'm looking at this part of the graph headed forever left. Well, since it's a horizontal line, I'm already at the y value a, so that's where it's headed. Now the next one. What if I'm headed towards the right of the graph? So towards the right of the graph, that means that x is headed towards, I'm going to write it in another color. That means that x is headed towards positive infinity, which is this arrow. And so where is f of x headed towards? It's headed towards a as well. And it's the same thing for this arrow and the same thing for this arrow. So if you notice, for a horizontal line, we don't have any x-intercepts and we don't have any turning points. So turning points again are the hills and the valleys. So no hills and valleys here. Linear function. So linear function says f of x is equal to ax plus b. So some of you might get all bent out of shape. You're like, Murga, I remember it's m. So I'm going to just put here that technically this a that we're treating here is the m, and it is the slope. But again, the a that we're using here is this a right here. So that's the reason why we're using a and not m. Okay, so the degree is 1. Where did the degree of 1 come from? The degree of 1 is because it's technically x, and I can zoom in here. The degree of 1 is because it's technically x to the understood power of 1. So that g is in the way, but I'm going to fix it. I don't want it to confuse anybody. To the right. And so here I have to the understood power of 1. Or actually, I should put it in pink since I did the other one in pink as well. To the absolute power of 1. Okay, so the graph is a line. It's not horizontal or vertical because, again, the a can't be 0. And then here, let's see, it has 1 x-intercept and 0 turning points. So we've done lines for a while now. And so I can have a line with a positive slope. So I'm going to put here slope, which is my m, which is my a, is positive. So another way of saying that your a is positive is that a is bigger than 0. And yes, I do have 1 x-intercept. I have it right here. I'm going to pick another color here. Excuse me. These allergies. Just going to pick this one. I have too many colors I can't pick. So I have 1 x-intercept. And we are always increasing. My 3 little dots mean therefore I have 0 turning points. Now for the rest of these, it's technically going to be 0, capital T, capital P for turning points. Now the other graph that I can have is technically one with a negative slope. So coming like this. So my a is negative. And again, the way that we can write that is that your a is less than 0. And I do have 1 x-intercept right here. And this is always decreasing, so therefore 0 turning points as well. Okay. The next one. Oh, well, not quite yet. So hang tight. So let's see, we did the degree, we did that the graph is a line, it has 1 x-intercept, and it has 0 turning points. Now the end behavior. Again, the end, so this is going to be new, I shouldn't say again. So let me highlight this. This is a brand new concept. You've never seen it before. End behavior is where the y values of the arrows are headed. So if a is greater than 0, which means that your a is positive, which in this case is your slope is positive, then the left of the graph. Okay, so let's highlight here. Hang tight. All right, so the left of the graph, so for when a is greater than 0 and the left of the graph, that means that I'm going to be on this graph and this arrow right there, because my a is greater than 0. So let me make sure that you know that I know that you know. So for a is greater than 0, I do not want that. Sorry. For a greater than 0, that means that I can only look at this graph. right here. And so the left of the graph, where are my y values headed? Well, my y values are headed forever down. So it's going to be forever down. And we write forever down as negative infinity. And the right of the graph is going to be, yeah, that's good. This part of the graph, and I'm going to highlight it here, and it's going to be going forever up. Again, I'm talking about down and up because they're the y values. So this is going to be, excuse me, forever up. And this is going to be infinity. Now, for a less than 0, that means that I am going to only be looking at the graph where your a value is less than 0, which in this case, since it's a line, it's where our slope is negative. So I can only look at this graph right here. Okay, so the left of the graph on a good day is going to be, let me make this lighter. It is light. This part of the graph right there. Gosh, that's way too close to purple. Sorry, make it a little bit darker. Okay, better. So that's the left of the graph. And so it's headed forever up. So forever up is going to be infinity. So I'm taking this really slow, really slow. And the right of the graph is going to be this arrow right here. And for that, the graph is going forever down. So that's going to be, and I wish I had that color, negative infinity. So let me just make sure that you know that this one is forever down. And this one is forever up. Sorry for the background noise. Okay, so for a quadratic. So we know f of x is another name for y is equal to ax squared. And so now from here on out, the degree, which is 2, which is the highest power, is going to be nice and obvious. So quadratic function is equal to ax squared plus bx plus c. And a can't be 0 because if it is, then your x squared goes away also, and then you're left with a line, and that's not a quadratic. So the graph is a parabola opening upward if a is greater than 0, or downward if a is less than 0. And we should remember that again from our transformations and our studies with from parabolas as well. Okay, so let's do some graphs here for if a is greater than 0. So if a is greater than 0, I can have a parabola looking like this. And let's analyze it. Let's look at the x-intercepts and the turning points. So it has 2 x-intercepts. And it has 1 turning point. So the turning point, again, is where it changes from increasing to decreasing. And we can put here, right here is the turning point. So it has 1 turning point because it was decreasing and then it changed to increasing right at that point. Now, we can also have a is less than 0. So if a is less than 0, we can have this type of graph right here. And so there's an infinite possibility of graphs, but here it's just so you can have an example of the different turning points and x-intercepts. So this graph only has one x-intercept because it touches the, x-axis only once. And that point actually also happens to be the one turning point as well. And we can have another kid here. Let's make this one also a less than 0. But we can put the kid right here. And so it too also has one turning point right here. But if you notice, it doesn't cross the x-axis. So this one has 0 x-intercepts. Because they're imaginary, because they're not crossing the x-axis. So here, we did the degree, already explained that. We did examples if they're greater than or less than 0 for your a values. And it can have exactly 0. So we already had a kid with 0 x-intercepts, 1 or 2 x-intercepts. We have a kid for each one. And so now the new concept again of end behavior. So end behavior where a is greater than 0. So for a greater than 0, I can look at this kid right here. And all of the parabolas that have an a greater than 0, which are positive, have this end behavior. So for a greater than 0, the left of the graph, it's a different green, but okay, is this one right here, this arrow. So where are your y values headed? They are headed forever up. So let me put this here. This is going to be forever up. And the right of the graph on an a great, no. On an a greater than 0 type of graph, the right of the graph is this arrow here. And so where are my y values headed? They're also headed forever up. Now for an a less than 0 type of kid, I can look at either one of the two that are left. I'll just do this one. But you'll notice that the behavior is the same. The end behavior is the same, I should say. So for the left of the graph, let me just make sure it's not dark. For the left of the graph, it's going to be this arrow here, or this one too. Why not? Let's not leave that kid behind. Excuse me. And so the arrows are going forever down. So again, for the y values, you're going to be either saying up or down. So for this one, it's going to be negative infinity. Excuse me. And for the right of the graph, it's this arrow because it's the rightmost part of the graph, or this one for this kid. And it too is going forever down. All right, so a cubic function. So f of x is equal to ax cubed plus bx squared plus cx plus d. And a can't be 0 because if the a is gone, then we're left with a quadratic, and it's, or a line, if the b is gone as well. So we can't have the a equal to 0. So the degree is 3. So again, degree, highest exponent. And we have here that it can have 1, 2, or 3 x-intercepts with 0 or 2 turning points. So let's have some kids here where we can, as examples, where we can see how this is happening here. So for the cubic function, we can have this right here. That is not what I wanted again. This right here is a cubic function. And so we're going to put here that a is greater than 0 for this one. And in case you haven't seen a cubic, let's go over here. Sorry. So let me just put x to the power of 3. So there it is. That's what it looks like. And let's look at the x-intercepts. So it crosses the x-axis once. So I have one x-intercept. And this one is always increasing. Therefore, it has 0 turning points. So I'm going to put them in purple. Because I like my colors. All right. So there's one kid that we had. Let's have the same type of kid, but now with some hills and some valleys. So this kid is still a greater than 0. And it has 1, 2, 3 x-intercepts. And it has 1, 2 turning points. And again, turning points is where it changes from increasing to decreasing. Now let's have another kid. Just different examples here again of what you can have. Let's start having an a less than 0 type of kids. So for this one, my a is less than 0. I have 1, 2 x-intercepts. And I have, I should zoom in here. I have 1, no, not there, sorry. I have 1, 2 turning points. Let's have another kid. Excuse me. So here the kid is a is less than 0. Again, it's a reflection of the parent function. We have x is equal to 1 turning point. Excuse me, x is equal to, oh my goodness. My x-intercept is 1. So I have 1 x-intercept. And I have 0 turning points as well. Just like the first one. The first kid. 0 turning points. This thing is always decreasing. And our last kid, just for the sake of having another graph here. So here my a is less than 0. I have 1, 2, 3 x-intercepts. And I have 1, 2 turning points. That's a cubic. So now let's analyze the end behavior here. All right. So for a greater than 0, that would be this graph. it would be this graph, and that's it. So the left of the graph is the leftmost arrow, so it's that one or that one, and that's it. And so it is going, forever down. So forever down is going to be negative infinity. And the right of the graph is this part here, and it's this part here. It is going to be going forever up, which is positive infinity. For a less than 0, that's going to be the rest of the graphs. So I can just circle them there. And so for the left of the graph, I am looking at, why does it change the opaque? I'm looking at this arrow or this arrow or this arrow. If you notice, they're headed in the same direction. They're headed forever up. So forever up is going to be infinity. And the right of the graph, which is this arrow or this arrow or this arrow, are always headed forever down, which is going to be negative infinity. And I forgot to color this one for the right of the graph. Okay, a quartic function. So a quartic function, the degree is, highest power is 4. So the degree is 4. And again, a can't be 0, because if the a is a 0, then the first term is gone and we're left with a cubic or so on and so forth. So let's see. Let's have some kids here that look like a quartic. So let me show you a quartic in case you haven't seen it before. So this is x to the power of 4. And if you notice, it looks a lot like a quadratic. If I wanted to, I could do x squared. So there's an x squared and there's an x to the 4th. Okay. Oh no. Okay. So we're going to have different type of quartic kids here. And so one of them can look like this. So here my a is greater than 0. I have one x-intercept. And I have one turning point. It's the same one. Again, turning point is when it changes from increasing to decreasing. It's the hills and the valleys. So one turning point. We can have another kid here. So for this one, my a is less than 0. Again, it's a reflection. And I have 2 x-intercepts. And I have, I'm going to zoom in here. I have 1, 2, 3 turning points. The next kid that we can have here, let's have this one. So for this one, my a is greater than 0. I have 0 x-intercepts. It's not crossing the x-axis. And I have 3 turning points. 1, 2, 3. Oh, that's not what I wanted to do. For our next kid, I can have so for this one, my A is less than 0. Again, it's upside down, it's reflected. And here I have 1, 2, 3, 4 x-intercepts. And I have 1, 2, 3 turning points. And for the last kid, we can have something like this. So for this one, my A is greater than 0. I have 3 x-intercepts. 1, 2, 3. And I have 3 turning points. 1, 2, and 3. So now let's look at end behavior. So if we have A is greater than 0, so for A greater than 0, I can be looking at this kid or this kid or this kid. Okay, so the left of the graph. The left of the graph is this arrow or that arrow or that arrow. For all 3 of those kids, that left of the graph is headed forever up. Now the right of the graph, here's the right of the graph. It's a little bit too dark. That right of the graph, or that one, they're all headed forever up. Now for A less than 0, which are the remaining graphs, so this one or this one, the left of the graph is that arrow or that arrow, and it's headed forever down. So it's going to be negative infinity. And the right of the graph is that arrow or that arrow, and it's also headed towards negative infinity. And I forgot to highlight the other purple. There we go. The kinetic function. So the kinetic function, let me introduce you to it in case you've never seen it before. So it looks like an x to the, it looks like an x to the third. Let me graph an x to the power of 3 here. There's an x to the third, there's an x to the fifth. But there's a kinetic function right there. All right. So for the kinetic function, the degree kinetic for 5, the highest power, so it's a kinetic. And you can have 1, 2, 3, or 4, or 1, 2, 3, 4, or 5 x-intercepts, and 0, 2, or 4 turning points. So let's have some kids here. All right, so we said it looked a lot like a cubic. So here we go. And so for this one, our A is greater than 0. We have 1 x-intercept. and we have 0 turning points because always increasing. The next one, oh, my turning points were in purple. Take out your cell phones and start texting. Or fast forward, actually. Huh. Okay, another kid here that we can have. This one right here. So for this one, we can say that our A is still greater than 0. We have 1 x-intercept. But in this case, we have 2 turning points. Another kid that we can have, something like this. Our A is greater than 0 still. We have 2 x-intercepts. And we have 1, 2, 3, 4 turning points. Another kid that we can have is this one right here. Our A is still greater than 0. We have 1, 2, 3, 4, 5 x-intercepts. And we have 1, 2, 3, 4 turning points. And the last kid that we can have can look something like this. So here our A is less than 0. We have 1, 2, 3 turning points. 3 x-intercepts, And we have 1, 2, 3, 4 turning points. So now let's analyze our end behavior. So for A greater than 0, we had 4 kids that had A greater than 0. These right here. So the left of the graph, we were using green. So the left of the graph of these kids is that one, or that one, or that one, or that one. They are all headed towards forever down, which is negative infinity. And then the right of the graph is that part of the graph, that part of the graph, that part of the graph is headed forever up. And for A less than 0, we just had 1 kid, which was this one. And so for the left of the graph, it's that part of the graph right there. And that's headed forever up. And the right of the graph is that part of the graph is headed forever down. Now to look for some general observations here. So general observations. So the end behavior. And we want to look for even powers of x. So even powers of x, and we specifically want to look for a greater than 0 type of graphs. So for even powers of x, for example, we have x squared and x to the 4th. So here I'm going to go back here. So this right here is even power. And this one right here is also an even power. And we're only going to look at a greater than 0. So if you notice, I'm going to highlight it here with this one, I guess. I want another one. With this one. So for this a greater than 0 and this a greater than 0, if you notice, the left of the graph is headed towards infinity and the right of the graph is headed towards infinity for this entire, for both even powers. So the left of the graph is headed towards infinity and the right of the graph is headed towards infinity. And the same thing with the a less than 0. Well, let's do the a greater than 0. So hang tight. So for a greater than 0, let me write this down. Sorry. Okay, now I'm having way too much fun with my colors. So for even powers, no. Okay. So as x heads towards infinity, which is forever, right? Your y values, which is f of x, is headed towards infinity as well because they're headed forever up. Now, as your graph is headed forever left, which is as x heads towards negative infinity, then your graph is headed forever up. So that means that f of x is headed towards positive infinity. And that is technically what we just highlighted here so maybe I should just circle it. I'm afraid of having too much highlight. This one right here. And this one right here. Now for a less than 0, so let's take a look for a less than 0. So for a less than 0, for even powers only, I'm looking at these. And if you notice, both the left and the right of the graph are headed towards negative infinity. And the same thing is the case right here. Okay, so let me write it over here. So for a less than 0, we had that as x goes towards infinity, which is forever, right? Our y values are headed towards negative infinity because they're headed forever down. And then as x heads towards negative infinity, which means forever to the left, then our y values are headed forever down. I shouldn't put a cup. These are separate. Okay, now odd powers of x. So odd powers of x, we can put them another color here. So odd powers of x are going to be this one, like a quintic. So it was, we had x to the fifth, we had x cubed, and technically we had x to the understood power of 1. Because, here we go. So these are going to be odd. So this is going to be an odd power. This one's going to be an odd power. And even this one's going to be an odd power. So if we look at all of these odd powered type of functions, the linear, the cubic, and the quintic, for a greater than 0, we're gonna see now I have way too much color here. For a greater than 0, what? All that work and it didn't change. I wanted this one. Okay, so did it change it? Yeah, it did. So for a greater than 0 here, and it looks exactly like almost, oh my god. All right, way too much time on the color coding here. So it's headed, for the left of the graph, it's headed forever down, and the right of the graph is headed forever up. And this is for a greater than 0s. Be nice to me, technology. Come on, you can do this. Okay, I need it. So the same thing, excuse me, if you notice for the cubic, for a greater than 0, the end behavior is the same. Left of the graph is negative infinity. Right of the graph, the y values are headed towards positive infinity because they're headed forever up. And the same thing for the quintic. Excuse me. Okay, so let's write down what we just said here. So here on this one, as x heads to infinity, which means forever to the right, then our y values are headed towards infinity because they're headed forever up. And as x heads towards negative infinity, which is forever left, our y values are headed forever down. And that's for odd powers of x where your a is greater than 0. Now, where a is less than 0, so technically since I did all of the a less than 0s blue, doesn't want to take it off anymore. I'm sad. Oh, now I did. I just circle it blue. So now for all the odd powers of x where my a is less than 0, okay, way too much time on the color, but here I go anyway. It's this one right here. So the left of the graph, as your x's head towards negative infinity, it's going forever up. And the right of the graph, as x is headed towards forever to the right, the graph is going forever down. And that is the case for all odd powers where your a is less than 0. All right. And here we go again. Be nice. Okay. So, as x heads towards infinity, which is forever, right? Your y values are headed towards negative infinity because they're headed forever down. And then as x heads towards negative infinity, which is forever left, then your y values are headed towards positive infinity because they're headed forever up. Now this next sentence, it'd be nice if we can come up with the fill in the blanks here, but it says the graph of a polynomial function of degree n with n greater than or equal to 1 has at most blank x-intercepts. So if I look at the kintic, the degree is 5, and the highest number of turning points is 4. If I look at oh my goodness. If I look at a degree 4 function, the highest number of turning points is 3. If I look at a cubic, the highest number of turning points is a 2. If I look at a degree 2, the highest number of turning points is exactly 1. And if I look at a degree of 1, I have 0 turning points. So if you notice, it's always 1 less than whatever the degree is. Oh my. So here on this one, this is going to be n minus 1, x-intercepts. Oh, and I was talking about turning points, right? Sorry. So this is n minus 1 turning points. I was talking about turning points. For x-intercepts, so let's see. So for x-intercepts, let's do, so the degree is 5. Oops. The degree is 5. Be nice. And the x-intercepts is 5. For degree of 4, I can have 4 x-intercepts. For a degree of 3, I can have 3 x-intercepts. For a degree of 2, I can have 2 x-intercepts. For a degree of 1, I can have 1 x-intercept. So for this one, be nice. This is going to be n x-intercepts, whatever your degree is. So let's do these examples. Find the number of turning points. So the turning points for this graph is 1, 2, 3, 4. A has to be greater than 0 because all of the end behavior of technically cubics and quintics, when your arrows are headed in this direction, your A is greater than 0. The degree, is it even or odd? So it has to be odd. And the reason why it's odd, there's something that I need to tell you here that you need to know that I need to know that you know. Is if you look at the even powers of x, the x squared and the x to the fourth on the graph, they both have their arrows pointing in the same direction. They're either both going up or they're both going down. And that's going to happen with all even powers. Odd powers are one side's going to be going down and the other side's going to be going up, or vice versa. So for this graph, one side is going down, the other one's going up, so it has to be odd. Now, the minimum degree is the lowest degree that it can be. So on this one, okay, so it can't be a cubic, because a cubic, if I go back here, a cubic can have at the most 2 turning points. And this one has 4 turning points. So the lowest that it can be, based on what we have here in this formula, technically is that it's going to be 5. The minimum degree is a 5. Because 5 minus the 1 gives us the 4 turning points that it has. So that's the smallest that it can be. It could be a degree 7. It could be a degree 9. But the minimum degree is a 5. All right, number 2. State the degree and leading coefficient of f. So the degree is 3. And the leading coefficient is -2. So the end behavior, it'd be nice, especially if math is in your future, that you can look at an equation and say, oh, okay, because the degree is 3 and the leading coefficient is -2, using these two things, I know that my end behavior is going to be like this and like this, with something going on here that we're not sure. We don't know if it has hills, valleys, or not. Now, that's the graphical representation, but the end behavior in symbolic and algebra, and written in mathematical terms, I should say, is that as x heads towards -infinity, f of x heads towards infinity. And as x heads towards infinity, which is forever right, my y values, which are f of x, are headed towards -infinity. And that goes using this table that we just did up here up at the top, this one. So odd power, my a is negative. It should mirror this right here. And it does. So for B, my degree is a 4. My leading coefficient is a 3. So all even powers, and this is technically positive. My end behavior is going to be like this. So let me cut this off. I'm not sure what's happening here as to hills and valleys. So using that graph, then as x heads towards forever left, my y values are headed forever up. And as x heads towards forever right, my y values are headed forever up.